In this video, we will look at some more applications of Bernoulli's equation and how it applies to situations that we'll see in our day-to-day life. This follows along in section 11.9 and 11.10 in your textbook, going all the way through the end of the chapter. Once again, Bernoulli's equation, the pressure plus the kinetic energy plus the potential energy is equal to some constant. So here we have the pressure at some point plus 1/2 the density times the velocity at that same point plus the density times acceleration due to gravity times the height at that same point is equal to some constant, which in this case is the same as the pressure, the kinetic energy, and the potential energy per unit volume at the second point further along within some pipe. So once again, energy is conserved. The major consequence of Bernoulli's equation is that as the speed increases, the pressure decreases. And this has a lot of applications to our modern life. We look at an airplane wing. The faster the air travels over, the pressure decreases. The more it decreases. Therefore, there's a difference in pressure, and that actually is what generates part of the lift and that's what generates the lift for an airplane. This is something that is very it's non-intuitive. It kind of goes against your normal thinking. The faster something goes, the less the pressure is, or the more the pressure decreases. So this is going to be, I think this is one of the hardest things to kind of grasp and understand.
First, I will show you an example whereby I keep y constant. So I have a tube which changes diameter, but the tube is not changing its level y, as I do there. So I come in here, cross-sectional area A1, I widen it, cross-sectional area A2. This is y, it's the same for both. I have here inside pressure P1, and here inside I have pressure P2, and this is the density of the fluid. There is here a velocity V2, and there is here a velocity V1. And clearly V1 is way larger than V2, because A1 times V1 must be A2 times V2, because the fluid is incompressible. So the same amount of matter that flows through here in 1 second must flow through here in 1 second. And so these have to be the same. Since A1 is much smaller than A2, this velocity is much larger than V2. Now, I'm going to apply Bernoulli's equation. So the first term tells me that 1/2 rho V1 squared. I can forget the second term because I get the same term here as I get there, because I measure the pressure here and I measure the pressure there. They have the same level of y. So I can ignore the second term. Plus P1 must be 1/2 rho V2 squared plus P2. That's what Bernoulli's equation tells me. Now V1 is larger than V2. The only way that this can be correct then is that P1 must be less than P2. So you will say, big deal. Well, it's a big deal, because I would have guessed exactly the other way around, and so would you. Because here is where the highest velocity is. And all our instincts would say, oh, if the velocity is high, there's a lot of pressure. It's exactly the other way around. Here is a low pressure, and here is a high pressure, which is one quite bizarre consequence of Bernoulli's equation. You must all have encountered in your life what we call a siphon. They were used in the medieval and they're still used today. You have here a bucket. In general is used with water, lakes. We have water here, but it could be any liquid. And I stick in here a tube. It's a smaller diameter, substantially smaller than this area here. And there will be water in here up to this level. This level P2, Y2, this is Y1, increasing value of Y. This height difference is H. P2 is 1 atmosphere. I put a 1 there, it's atmosphere. And here, if it's open, then P1 is also 1 atmosphere. So there's air in here, and there's liquid in here. I take this open end in my mouth, and I suck the water in so that it's full with this water, And strange as it may be, it's like making a hole in this tank. If I take my finger off here, the water will start to run out, and I will show you that. And you have here a velocity, V1. The water will stream down into this here, and the velocity here is approximately 0, because this area is so much larger than this cross-sectional area that, to a good approximation, this water is going down extremely slowly. Let's call this high difference D. I apply Bernoulli's law. So now we have a situation where the Y's are different, but the pressure is the same, because right here, at this point of the liquid, I have 1 atmosphere, which is barometric pressure, and since this is open with the outside world, P1 is also 1 atmosphere. So now I lose my P term. There I lost my Y term, now I lose my P term. So now I have that 1/2 rho, this is rho of the liquid, V1 squared, plus rho G times Y1, must be 1/2 rho V2 squared, but we agreed that that was 0, so I don't have that term. So I only have rho G Y2. I lose my G's. No, I don't lose my G's. 1/2 rho V squared, no, that's fine. And so I lose my rho. This is 1/2. I lose my rho. And so you get that 1/2 V1 squared equals G times Y2 minus Y1, which is H. And so what do you find? That the speed with which this water is running out here, V1, is the square root of 2GH. And you've seen that before. If you take a pebble and you release a pebble from this level and you let it fall, it will reach this point here, this level, with a speed, the square root of 2GH. We've seen that many times. So what is happening here, since the pressure terms are the same here and there, now there is only a conversion. Gravitational potential energy, which is higher here than there, is now converted to kinetic energy. This siphon would only work if D is less than 10 meters. Because of the barometric pressure, you can never suck up this water. No one can. Vacuum pump can't either, to a level that is higher than 10 meters. When I did the experiment there with the cranberry juice, I was able to get it up to 5 meters, but 10 meters would have been the theoretical maximum. So this has to be less than 10 meters that you go up. If I would have made a hole in this tank here, just like this, down to exactly this level, and I would have asked you to calculate with what speed the water is running out, you would have found exactly the same if you applied Bernoulli's equation. This is a way that I've seen people steal other people's gasoline in the time that gasoline was very scarce and that there were no locks yet on the gasoline caps. You would put a hose in the gasoline tank, and you would have to suck on it a little. You have to sacrifice a little bit. You get a little bit of gasoline in your mouth, and then you can just empty someone's gasoline tank by having a canister or by having a jerry can and fill it with gasoline. And I'm going to show that now to you by emptying, that's still cranberry juice, by the way, from our last lecture. So let's put this up on a stool. So there is the hose. It's that thing. And I'm going to transfer this liquid from here to here. So first I have to fill it with cranberry juice. And there it goes. And as long as this level is below that level, it keeps running. Not so intuitive. I remember I was at a summer camp when I was maybe 6 or 7 years old. I couldn't believe it when I saw this for the first time. We had these outdoor sinks where we washed ourselves and brushed our teeth. And the sink was clogged. It was full with water. And one of the camp leaders took a hose, sucked up, and it emptied itself. And I really thought, you have to take spoonfuls of water or maybe buckets and scoop it out. This is the way you do it. Very non-intuitive. The non-intuitive part is that it runs up against gravity there. So we can let it sit there, and we have a mass transfer of cranberry juice.
Using this diagram on the right side here, I want you to please answer what would happen based on the two different pressures to the gas in that container. Second, why is there a low pressure in the tube where the air is flowing? Use Bernoulli's equation and the Bernoulli's idea to explain why there's a low pressure there. Thank you very much and have a good night.